title of the talk is Modern Big Data Analytics Tools. Essentially, I'll be talking about what I've witnessed over the last 10 years as to how enterprises have changed how they analyze a lot of data that they have been collecting and storing. Okay? And most of that talk and most of that tool stack is actually based on Apache Hadoop. So I will mostly be talking about that. Right? So I've been working now in the industry for more than 20, 25 years. I would say about half of my career in the initial half was spent in high-performance computing, and the later half in so-called big data analytics systems. And at the end of the talk, I'll show how both of those have sort of begun to coalesce around in the same platform. Okay. So nowadays, of course, my claim to fame is that I'm a Hadoop midwife. I was present in Yahoo when Hadoop was delivered, and I actually helped deliver it. So let's start with a story. Once upon a time, just about 15 years ago, a long time, not a long time ago, but in a land really far, far away, there was one database, one relational database that ruled them all, right? Fast forward 15 years now, and suddenly we see that there is a landscape of databases. And 95% of these databases that are on this map are actually originated in the last 10 or 15 years. Okay? So what happened? I mean, why did we need to move from one single relational database in a company to all these different kinds of databases which are suitable for different workloads, different kind of data streams, data types, et cetera, right? One of the major things that happened was the so-called Web 2.0, right? The Web 1.0 way of just displaying banner ads was no longer thought to be a viable business model. And more relevance came into the whole ad-supported web, right? Collecting data about the user's behavior, the visitors to your website, and analyzing that in order to determine what the user is interested in, that became the primary focus of this whole Web 2.0 thing. The second thing that happened was essentially mobile, right? I mean, you're carrying something in your pocket that could not exist 20 years ago was available. That kind of compute power was available only in supercomputers and things like that, right? And it is always connected, and it is always transmitting data about your activities, about your preferences, about what you do on that phone, and not only as a phone, but with all these applications and things. The third thing that happened is essentially the rise of social networks. Okay? And suddenly graphs became an interesting data type to analyze. Okay? Basically, see from Twitter all the way to LinkedIn, Facebook, everything basically are the core of that. All the algorithms that they use is graph analytics. Okay? And now what we are seeing is basically sensors everywhere, right? And not only in your pocket in terms of your phone, but especially in industrial settings, right? A single flight from across Atlantic actually generates something like 30 terabytes of time series data about the engines themselves. The rest of the data obviously is thrown away, but the engine data is actually stored and analyzed. Okay, so what that has led to is something that we nowadays call big data. And whenever I say big data, I always say quoted big data because nobody really knows what it is, right? It's not just the 3 V's as Eli spoke to you about. It's how you use the data. It's not the volume that matters anymore, right? But the biggest thing that happened in terms of all the database landscape to change was open source, okay? Linux was, I think, the first successful open source product to come out in the market. But really, for you and me, for the ordinary developer, right, really what gave the power of open source out is when Mozilla was open sourced, right? Netscape essentially open sourced Mozilla, right? That is when really things started to turn around 98, 99 timeframe. And now we basically see a lot of these core data infrastructure is actually based on open source, right? So based on all these developments, essentially what happened was that the traditional databases or traditional way of analyzing data was deemed to be too restrictive, right? And suddenly there was a system called Apache Hadoop that contained a distributed file system called HDFS and a distributed computational programming paradigm called MapReduce, right? That is it. That was the turning point in this whole database landscape to change. And suddenly, in the blink of an eye, in the next, after Hadoop was developed, in the next 5 years or so, suddenly you basically see there is a huge ecosystem of data products that have been built around the distributed file system, essentially. You already have the MapReduce and their new incarnations in These and Spark. Basically got analytical SQL engines being developed on top of Hadoop. You had distributed key value stores being developed on top of Hadoop. You had the whole management platforms for managing the whole plethora of projects that you got on this platform. And that process is what I'm going to talk about as to how that data analytics process evolved, and as a result, the platforms actually evolved to deal with the data analytics process. So when I talk about the Hadoop ecosystem, from 2003 to 2010, I refer to it as the historic period for the Hadoop ecosystem. Obviously, if you have heard about Hadoop, you already probably know that Hadoop is based on the two seminal papers that came from Google. One was called the Google File System, and the second one was the MapReduce programming framework that used, or that was co-developed for running large-scale data analytics on top of the Google File System, right? Around the same time, Yahoo had acquired a company called Ink2Me and Overture, and essentially bundled their products together and made it into Yahoo Search, okay? So in Yahoo Search, the content system, which is the search engine backend, which crawls the internet for web documents and then which indexes them, determines the relevance of those web pages, et cetera. So that came from Ink2Me, and Overture essentially was the ad engine that ran on top of that. So one of the projects in 2004-2005 timeframe that Yahoo Search launched was called W1W, Web Map in 1 week. WebMap was Yahoo's equivalent or Yahoo's version of PageRank in Google, right? So as the number of documents on the web exploded, as the number of documents that were crawled by the Yahoo search engine exploded, the WebMap building used to take something like 6 weeks. Okay, so by the time the new document appears on the web, it will take 6 weeks to get it into the search engine index. The goal for the W1W project was to actually build it in the whole web map and refresh it every week, okay? So there was an infrastructure for building web map at Yahoo at that time that was called Dreadnought. It was actually running pretty well on about 600 machines, right? But 600 machine scalability was not enough for doing the W1W project. And that is why Eric Bollschweiler, whose picture you saw on the last slide, he started a team that basically said, we are going to revamp this infrastructure for building the web map. And that project was called Juggernaut. So in Juggernaut, since we already had blueprints from Google for Google File System as well as Google MapReduce, we essentially launched on the similar path saying, we'll develop Juggernaut File System and Juggernaut MapReduce framework, and we'll use an open source project called Condor from University of Wisconsin to actually launch these batch analytics on the web documents in the Juggernaut framework, right? We worked on it for about 6 months or so. We had a working implementation at Yahoo at that time for Juggernaut. And then we came across this project that was being already developed in the Apache Software Foundation. It did not have a name then, but it was actually a sub-project of Lucene and Nutch. Nutch was the content system for the open source search engine called Lucene. And Doug Cutting, who had started both these projects, Lucene and Nutch, Yahoo hired him as a contractor to help us separate out what was the Nutch MapReduce and the Nutch distributed file system in Nutch to be a separate component, separate Apache open source project, so that Yahoo could contribute to it. Because Lucene and Nudge being open source search engines, and Yahoo already had a proprietary search engines, so Yahoo could not, or Yahoo engineers could not contribute legally to Lucene and Nudge. And that is why when Hadoop was separated out, which had nothing to do with search engine after that, then Yahoo engineers could start contributing to that. At the time, we started contributing to Hadoop, and which is essentially the Nudge distributed file system, and the Nudge MapReduce became Hadoop. It was successfully deployed at least one installation, which was the Internet Archive. It was analyzing something like 20 terabytes of data. About 3 months after we started contributing to Hadoop, we actually had it installed on a 600 machine cluster that we called Kryptonite. Okay? And since then, by the time I left Yahoo back in 2010, Yahoo had something like 45,000 machines running Hadoop, deployed with Hadoop. All right. So while the Hadoop development was going on, obviously the database technologists or database researchers took notice of it. Right? David Dewitt and Mike Stonebreaker, very famous researchers, very well-known researchers in the parallel database community, actually wrote that MapReduce is a major step backwards from the current database technologies because it does not do this, does not do that, et cetera, et cetera, et cetera. Right? If you look for this article now, it is actually gone. It is nowhere to be found on the web. Probably Internet Archive will have a copy of it. But on the system side of things, right, the people who actually built MapReduce and Google file systems, et cetera, they were actually praised in the systems community. And this is a quote actually from one of the anonymous system researchers at XLDB conference, basically saying that MapReduce is the revenge of system programmers because the database researchers will not consider them to be a true researcher, right? It's a revenge of those. So back in 2009 or something like that, a person named Tom White wrote this nice book, Hadoop: The Definitive Guide. I think it's on its third generation, or third revision now. It's a great book. If you go to O'Reilly's site now, this was actually back in 2013, you would see a number of books available from O'Reilly specifically to deal with the Hadoop ecosystem, specifically dealing with the Hadoop ecosystem. So this slide is from 2010, actually, as to show you how the Hadoop usage actually exploded in the enterprises. You would basically see that 2007, initially there were only a few brave companies that started using Hadoop, but then suddenly, if I go to 2013 or 2014, all the logos of all the companies that have either pilot projects going on with Hadoop or have Hadoop in production won't actually fit on a single slide. Okay, so the Hadoop usage has really, really exploded. And the entire industry has basically sort of shifted to work with Hadoop in some way or the other. Right? We have analytics infrastructure, you have operational infrastructure companies, you have storage companies, you have infrastructure as a service clouds. All of them somehow or the other are tied up with this Hadoop ecosystem. Right? So the Hadoop ecosystem, this is my favorite chart. There's a lot of vendors in this Hadoop ecosystem, and the arrows or the connections between those vendors actually show their partnerships, right? So if you can see, a lot of vendors are actually partnering with a lot of different Hadoop ecosystem vendors. So I like to call this a really promiscuous ecosystem because everybody sleeps with everyone else, right? Okay. So why did Hadoop become really so popular? If you go back, initial adoption of Hadoop, even for people who do not have the so-called big data problem, I think initial adoption of Hadoop in those companies was actually facilitated by the Hadoop economics itself. You just take a bunch of commodity servers together, you just latch them in a single cluster, right, with a commodity networking. You take this open source software, you deploy this open source software on that, and you are ready to go, right? So if you look at 2008, what the MPP database companies at that time were charging per terabyte, right? Something like $60,000 to $70,000 per terabyte of data, right? That has now really come down to around $1,000 per terabyte because of Hadoop, and even less. Actually, it's getting lesser and lesser, okay? But it was not only the economics. The analytics process within the companies also changed significantly. The earlier analytics process was basically, okay, you have a bunch of applications, and those are fronting the databases, and you are basically taking the transaction logs from those applications, and you are basically running a costly ETL cycle, the extract, transform, load cycle, and then loading it into your data mart and into your enterprise data warehouse. And portions of the enterprise data warehouse will be available to others, the data engineers, to play with in their own data marts, right? In that scenario, you were actually throwing away a lot of data in the ETL process itself because it did not actually fit your rigid structured model, right? What happened was that the single point which was ingesting all these data and trying to make it into a structured data was replaced by Hadoop. That was the first ETL offload was really the first application of Hadoop with most of these enterprises, right? So now, rather than doing ETL, which is extract the data from various sources, transform them to fit in some structure, and then load it into the data warehouse, we made it into ELT, which is extract the data from various sources, first load it in the raw form in your Hadoop infrastructure, and then transform it, and then put some of it in the data warehouse, okay? So Hadoop essentially parallelized the whole ETL process by making it ELT, okay? Now what we have seen is that with the rise of all the SQL and Hadoop engines, people are saying, why am I spending so much amount of money on the expensive data warehousing architectures when some of the non-mission critical stuff I can actually get done on my Hadoop cluster itself, right? So Hadoop cluster now has become your mini data warehouse, or actually, in terms of size of data, it is actually a mega data warehouse. But really, the non-mission critical analytics applications have now moved onto Hadoop. And as we can see, as we see the Hadoop ecosystem maturing more and more, we'll see more and more mission critical applications also running there, right? So in current enterprises, if you look at the Hadoop maturity curve, the late adopters or people who basically adopted Hadoop recently, they have been using it mostly for ETL offload. They're basically keeping all the data. I mean, this is where you call it data lake or whatever, but you're bringing in all the data from all available sources within your enterprise, keeping it in Hadoop, and then doing the ETL processing there, loading it into the data warehouse, right? And now more and more applications themselves, so rather than creating data marts, separate data marts from EDWs, because of the multi-tenant nature of Hadoop, you are moving the data marts themselves into Hadoop. And so if you give the data engineer access to your Hadoop cluster, he or she will basically do all its experiment on the raw data there that is stored in this data lake, right? I mean, these are all marketing terms, but they really stick, okay? What we have started seeing in the early adopters of Hadoop is new applications being built on top of this Hadoop infrastructure, right? Elias talk actually gave a very nice example of how they use Hadoop internally to do the customer support, ticket analysis, and things like that, right? So such big data applications are now being built on top of Hadoop. Where we see it going is that the entire enterprise, whatever the data warehouse applications were, those will slowly start moving onto Hadoop, and really this enterprise will become the data-driven enterprise, right? What we have seen so far, though, is there is a huge gap between what data you collect and what data you actually operationalize, or how much data you actually operationalize, right? So today's enterprises, you basically see, because of all this connectivity everywhere, 70% of the data in enterprises is interaction data with the enterprise and is actually collected, generated by the customers themselves. About 80% of that data is being stored, right? You throw away some of the bad data that you get, that's pretty much it. I mean, which is purported to have no value at all. That's the data you throw away, but 80% of that data you keep. But if you basically see how much data you are actually using for business decision making, it's just about 3%, okay? That's the state in most enterprises today, most non-web enterprises, I should say. And even among those 3%, I think only about 0.5% is basically analyzed and being operationalized, okay? So that's the big gap that Hadoop is actually trying to address, that all the data that you store in the Hadoop file system, for example, you should be able to analyze, and you should be able to prepare for analysis, analyze it, and operationalize it, okay? So how are companies or how are vendors trying to address this gap? The first one that people are trying to do is to make it friendlier for the storage administrator. The storage administrators in a typical enterprise is actually the most conservative administrator that I've ever seen, right? It's not like the application developers who basically say, okay, today I'm going to do Ruby on Rails, tomorrow I'm going to learn Node.js, and whatever is good for my application, I'm going to use that, right? The storage administrator is basically saying, oh, I've been using EMC or NetApp or Hitachi, the storage platforms for a while. It takes a while for them to get sort of familiar or comfortable with this new storage paradigm, the distributed direct attached storage, right? So what a lot of vendors are doing is actually expanding the capabilities of Hadoop distributed file system itself, but in addition, they're actually plugging their storage infrastructure so that it could be accessible by Hadoop, right? So we basically initially had only the Hadoop distributed file system. There was a competitor, a proprietary competitor called MapR file system that came along about 3 years ago. Now if you go to a storage vendor, they will have at least one product or two that will be compatible with their Hadoop file system, including EMC, NetApp, everybody has that, right? The second thing that we have started seeing is, since MapReduce was the only programming paradigm that ran on Hadoop maybe about 3-4 years ago, there was not a lot of talent available that would do MapReduce programming for you, okay? Initially, developers will basically just, Java developers in particular will be delighted so that their application can run on thousands of machines, and they will actually start learning about it. But when you went to actually the business analyst and data analyst, that community who was very familiar with SQL, it would be very hard for them. It has been very hard for them to move away from their SQL-based analysis and into the MapReduce programming paradigm. So what the vendors did is basically try to address that skills gap by saying, okay, we'll basically augment MapReduce by providing you a full SQL interface that runs directly on top of your Hadoop data, right? Cloudera came up with a project called Impala. Pivotal, my company, came up with a project called Hawk, which is essentially Greenplum's 10-year-old database technology running directly on top of Hadoop. And suddenly this space has now exploded. You basically, every month or so, you see a new announcement of SQL on Hadoop happening. How does the SQL on Hadoop really work? Well, the details are obviously different for each of the different SQL implementations, but really what you have in the HDFS, which is a data node, you will co-locate something called a segment server, or some people call it just a shard server or something like that, with the data node itself, right? And all that, the MPP SQL engine essentially is taking these SQL queries from the client, creating parallel execution plans, dispatching them to these individual segment servers or whatever you call them in the data nodes, and then they will go directly to the HDFS files and read from there and process it that way, okay? All right, so initial results for all these new SQL technologies that are running on Hadoop have been very encouraging. Before Impala or before Hawk, there was obviously one SQL-like language available on top of Hadoop MapReduce, which was called Hive. So Hive basically was a subset of, or is a subset of SQL that gets translated into a series of MapReduce jobs. And obviously, since MapReduce jobs materialize every intermediate data, even the data between MapReduce jobs, and in MapReduce itself, you have a materialization step, it was really slow. So the initial SQL engines who have been in this market essentially compared themselves against Hive. They basically, you'll see numbers like 40, 50 times faster than Hive, right? So now the batch-oriented SQL or batch-oriented computations really came to interactive computations, okay? Various, excuse me. So various database technologies or various MPP SQL engines have, excuse me. have different capabilities, right? The basic model of moving the computation to where the data is now being extended to analytics as well. So rather than taking data out of a database or a Hadoop system out to your analytics system, analyzing it, generating models or whatever, we are now trying to push more and more analytics into the database itself or into the Hadoop framework itself, right? So one of the open source projects that we have been doing at Pivotal for the last 4 years, along with a bunch of different universities, is called MADlib. MADlib, the MAD part of that actually stands for Magnetic, Agile, and Deep. And it's a set of analytics algorithms, set of machine learning. It's a machine learning library, but it actually runs inside the database, inside the data execution engine. So in terms of this entire Hadoop ecosystem, you would basically find that it is embedded in the SQL engine as a set of user-defined functions. Okay? What are the functions that are available there? Basically see a lot of machine learning, commonly used machine learning techniques like logistic regression, linear regression, k-means. So all of those are actually available. More than 30 algorithms are actually available inside MADlib. MADlib is open source, so you can go download it from there. MADlib runs inside Postgres, inside the Greenplum database, and inside Hawk, right? And I think there are a few experiments that people are doing to integrate it with Impala as well. So how do we invoke MADlib? We basically do a select star from something, the MADlib function, which is k-means, and feed it data that is actually stored in the database itself, right? So MADlib is not going to pull out data from the database, and it is not going to run on separate machines. It's actually going to be running in the execution engine of the database itself, right? So, but obviously, when you talk about machine learning, et cetera, then SQL may not be the right language in order to invoke all these libraries, right? The data scientists and the machine learning people are very familiar with R, for example. So what we have done is essentially created a plugin for R, which is the open source statistical language, so that we can actually access the MADlib functions directly from R. And this is available on CRAN, the R repository. You can download from there, right? So what happens in Pivotal R is that the interface is the R client. You can just use any of your favorite studio, favorite R programming environment, let's say R Studio or whatever, and you basically, the data does not leave the database, and you are pushing the execution of your R functions into the database, okay? It supports only a portion of R. It does not support all of R, okay? But a bunch of different a bunch of different MADlib functionality is actually available there, okay? So how does it work? All the data stays in the database, right? The R objects are essentially just pointers to those databases, right? All the model estimation and so let's say GLM function, all those things are the heavy lifting, heavy computational lifting is actually done by the MADlib function. So you just connect to the database, rather not through ODBC or JDBC and pull it, but actually connect it through the DB frames that are provided by MADlib and say execute the functions that are available, MADlib functions directly on those data frames. So as a result of that, it gets pushed deep into the database, executes there, and only the model is returned from the database, okay? All right, so where is Hadoop going? With the new refactoring of the MapReduce programming framework and its separation into two parts. One is the generalized resource manager and resource scheduler. And then the second part of it is the MapReduce framework that uses that resource manager and resource scheduler. So with that, now we can basically see from Hadoop 1.0, where MapReduce was the only programming paradigm that ran on top of Hadoop, we are going into a 2.0 model where Yarn is doing the resource management for your Hadoop cluster, and then multiple different applications, and even if I call them applications, these are actually programming frameworks that run on top of taking advantage of Yarn resource management. The multiple applications and frameworks actually run on top of Hadoop, right? So we're already seeing that happening. The way the Yarn architecture works is essentially it treats computational resources and memory in a single machine as if it's composed of multiple containers. And you basically, an application goes to the Yarn resource manager and says, give me up to 10 containers. And then Yarn gives the 10 containers back to the application. The application master, in that, after getting those containers, essentially deploys the software, whatever it wants to run there, deploys the software in those Yarn containers and start running. Right? So for example, for the MapReduce programming framework, the maps and the reduces, those tasks that now run inside, inside the containers, and what used to be the job tracker is actually the application master now. Okay? So just a little bit more about Yarn. Yarn stands for yet another resource negotiator. It basically has three major components. The resource manager I already talked about. The node managers are the daemons that are running on individual nodes and just manage the resources or the container life cycles for the containers that run on those nodes. That's pretty much it. Right? And the application masters are specific to a particular framework. So MapReduce has its own application master, what used to be the job tracker. Then we have a bunch of other application frameworks that are actually have their own application masters that work with Yarn. Okay? So as I was saying in the beginning, my first half of my career was in high-performance computing when we used to use a framework, high-performance computing framework called MPI, message passing interface, right? So over the last couple of years, what we have been doing is taking the MPI programming model and making it native to run on top of Hadoop. And this is the project that I call as Hamster. Hamster stands for Hadoop and MPI on the same cluster. So it's essentially an open MPI runtime that gets scheduled using Yarn, right? What Hadoop provides is basically access to data using the HDFS protocol and HDFS file system API, okay? Process monitoring by node managers, because each MPI process is now run inside its own container, okay? And that container lifecycle management is taken care of by Hadoop Yarn. It actually obviously provides the resource management and resource scheduling. What OpenMPI provides in this Hamster project is launching the processes, communication across these processes, and I/O forwarding. So STD out and STD in are basically forwarded in and out of those MPI processes. Okay, so MPI was never designed with knowing Yarn. Okay, Yarn came something like 10 years later, and we could actually make MPI run inside of Yarn. So that basically shows the power of this whole Hadoop ecosystem, that applications which were developed without any knowledge of Hadoop could easily be ported to run inside the Hadoop as a platform. What does Hamster get us when analytics are concerned? There are a lot of high-performance analytics libraries for specific models, specific data models, that actually use MPI as a communication mechanism, right? One such example is something called GraphLab. What GraphLab is basically, it's a graph analytics library. It's a set of machine learning tools that assume that the data underlying it is actually, fits actually the graph model. It was started back in about 5 years ago in Carnegie Mellon University. And recently, there is now actually a company that is founded to commercialize this, right? GraphLab has a bunch of different, very nice, very efficient algorithms, mainly for machine learning, like topic modeling, graph analytics like PageRank, and all those things are available. And now, with Hamster running OpenMPI inside of Yarn, there was no development work needed for GraphLab to be ported to Yarn at all. So you just took the open source GraphLab, and we just ran it over in the Hadoop distribution, right? So now you can basically see how more and more types of analytics are getting into the Hadoop ecosystem, and it is basically becoming a single modern analytics platform that is capable of handling multiple types of data and multiple scales of data at a multiple, I would say, latency expectations like batch, interactive, and even real time. Okay. So why do we want a graph lab to be running in a single cluster, in a multi-tenant cluster? Well, if you look at the analytics pipeline in a typical enterprise, it's not, even if graph is the central source of data or central model for that entire enterprise, only graphs are not enough. You basically have to take all this data that you are collecting from logs, put them, join it with the graph model, then do the graph analytics, then publish the model out, right? So you are already doing, earlier you were doing different types of analytics in different environments. Now with GraphLab, Hamster, Hadoop, Yarn, all these things in a single platform, actually you can do all types of analytics in this single environment, right? So what I'm going to leave you with is basically just a vision of whether this single platform will be the data platform of future. I think we are getting there. We basically already have batch and interactive analytics engines, and also taking clickstream data, taking all the interaction logs, taking graph data, all of that, putting into a single storage platform and working on it with multiple different execution engines. We'll basically see more and more in-memory type application workloads also moving into the Hadoop ecosystem. And really, to me at least, it looks like it is going to be the default modern data platform of future. Questions? You have about 5 minutes, something like that. No questions? I was either very, oh yeah, you have a question. Yes, the slides will be available. Yeah, I will put it on SlideShare. My SlideShare username is Hadoop, coincidentally. Yeah. Any more questions? Yeah. Yeah.
And I think I've heard of one other one somewhere else. Could you talk a little bit about what's going on at the file system level in this open source big data space? What's trending up? What's kind of been, legacy?
Sure.
And trade-offs?
Sure. So the question is about the whole, where the HDFS, the file system and storage space is going in this Hadoop ecosystem. I think there was one slide where I basically said every storage vendor out there is making their file systems, their scale-out parallel file system, their scale-out systems, even their block storages actually compatible with Hadoop. Now, the compatibility is actually achieved at various levels. Hadoop is has a public Java API. HDFS has a public Java API that you could basically just derive from file system API. And you could provide a file system API for your particular file system, right? The second way of making it compatible, and at least one vendor, EMC Isilon, has done that way, which is now that HDFS 2.0 has a protocol which is multilingual protocol defined in protobufs. So you can actually have a C client connecting directly to HDFS without having to go through the Java JNI route, okay? So that's the second way of making it interoperable. The third is actually looking, and this is a fairly recent thing, that you can keep your name node, you can keep your HDFS data node, right? But with the FS dataset service provider interface, which has become public, right? Now you can have your block storages and your object storage directly provide data, as in data node data, using that FS dataset SPI, right? So we'll see more and more integration of the traditional Hadoop, traditional storage vendors into the Hadoop ecosystem, right? That's one. Your question, although, was about Parquet and some other storage formats as well, right? I think the columnar formats for analytics is a given, right? Even the Pivotal Hawk that I showed, our Greenplum database using HDFS on top of HDFS actually uses Parquet. So in this latest release, we actually put our weight behind Parquet, saying that, okay, this is the right format for the analytical workloads, and it is going to get there, right? For other types of workloads, there are always going to be different kinds of file formats. So for example, HBase and the newer versions of HBase, as well as other key value stores, things like Accumulo, they have a file storage format which is specific to their needs, right? H file and H file v2 and H file v3, etc. Right? So depending on the use case, there will always be a file storage format which is optimized for that, right? What we'll see happening though, right, and this is again my guess, is that the storage connectors or the file format connectors will be available for each one of these different components, the top level components, right? So for example, Hawk is able to write and read from the Parquet format. That does not mean that the same Hawk data cannot be queried using a MapReduce format, MapReduce programming paradigm, right? Because we have a input format for the MapReduce, right? And then the same way, it will basically, there will be a connector for dumping taking the Parquet formatted data and putting it into H file so that we can bulk load it through HBase, right? So we'll basically see these connectors being developed across multiple formats. Yeah, sure. Sure.
So I guess RC file is another one, Parquet, and then not related to that, but then sort of the distributed file system world. You've got Ceph, and I guess a little bit talk on Orange.
Yeah.
Do you see these guys all kind of converging, or is this a space where people are competing with each other, active development? What's going on?
So good question. I mean, so the question is actually there are two parts in there, right? Parquet and RC file. I mean, these are all formats, right? And whereas the second part of your question, which is Safe and Orange FS, and basically it's all storage systems, right? So I think we are seeing. I mean, I'll address the second part first. I think we are seeing a lot of development, a lot of activity in the storage system. And it's not because suddenly people discovered that, hey, distributed file systems are the way to go, right? I think we have also seen a new player coming in the market, in the hardware market, to address that gap we had in the memory hierarchy, which is SSDs, right? If you look at the way the SSD prices are coming down, I think in a couple of years, it will be basically just, all SSD will be the norm, probably, at the rate that this is coming down, right? But today we are basically seeing that, okay, there is in memory, then in SSD, and then in hard disk, right? Whoever does the best job of scaling this out, as well as while keeping it performant, I think is going to win, right? HDFS is sort of providing an umbrella for analytical workloads of APIs, and there will be a lot of HDFS-like systems that will develop, addressing various kinds of workloads there. In the second, the first part of your question, which is Parquet versus RC file. So RC file was a modification of sequence file for structured data, right? It was basically the way you would it's a hybrid row columnar format, right? It went on for quite a long time since Hive came about. That was the format they used, right? Recently, Hortonworks and Facebook have basically implemented a new RC file format called ORC file, right? When we started looking, for example, for an optimized row columnar format for analytical workloads, we considered ORC file as well. But ORC file is basically very Java specific. The serialization is Java. Everything else is Java, right? Whereas in Parquet, we basically actually have a multilingual capability, right? So you have Hive can use Parquet format. There's a new SQL on Hadoop engine called Apache Tazo that can use Hive Parquet format. Impala can use Parquet format, and Impala is written in C, C++, I think C++. So that multilingual capability of accessing the same data in both Java as well as C and C++, that is extremely important to us, and that is why we went with the Parquet format, right? So in terms of Parquet and ORC file, my personal belief is that Parquet is going to win, okay? Any more questions? Actually, we are end of our time now. Thank you.